Okay, thank you very much. We have José Luis Cortés from Universidad Zaragoza, Relativistic, Deformed Kinematics, and as a signal of quantum gravity. Please go ahead.
Okay. It's a pleasure to have the opportunity to present this work at such a pleasant meeting. The message I want to convey here is that is the possibility that a signal of quantum gravity theory is the formation of special relativity, the formation of relativistic deformation of special relativity. We still do not have a complete consistent theoretical framework in incorporating these ideas. So then there are still many open questions, both from a theoretical and phenological perspective that some of them I will discuss during the talk. And also I would like to point out that the near future of high energy particle and especially astroparticle physics can open new possibilities to identify these observable effects of a deformation, of a relativistic deformation of special relativity, if it is a real effect. The talk is based on work in collaboration with José Manuel Carmona and José Javier Relancio from University of Zaragoza. I'm not going to refer to properly to other works during the talk, but you can find the references here in these two published works. Looking at the list of advanced topics of this meeting, I found four items which are related to this talk, which is astroparticle physics, Lorentz symmetry violation, particle physics, or quantum gravity and phenomenological implications. Okay, let me start by showing, or just by this very naive observation that there seems to be a conspiracy against the possibility to study or to make progress in the search of a theory of quantum gravity from a phenomenological perspective. This conspiracy is, comes from the fact that on the one hand, when you have a system where quantum effects become important, then the gravitational interaction becomes irrelevant, and the other way around. When the gravitational interaction is relevant, then in most, the quantum effects are irrelevant. Then this raises the question where to look for signals of a theory of quantum gravity. If you use the fundamental constants of relativistic quantum theory together with Newton gravitational constant, then the scales or the value of the scales you find lead you to think that the only possibility to have some observable effects of a quantum gravity theory requires to go to very, very extreme conditions, like for example, to go very close to the Big Bang or to the interior of a black hole. But these are situations where the possibility to, the possibility of observations, if any, are very, very indirect. Then let me just very schematically try to argue why to consider a relativistic deformation of a special relativity in relation to a theory of quantum gravity. Okay, a theory of quantum gravity can be thought as a theory of quantum space-time. I mean, just space-time is the basic ingredient in gravity. Now, going beyond the notion of classical space-time, then suggests that one should go beyond the symmetries characteristic of this classical space-time, and in particular, then one probably one can guess that an ingredient in a theory of quantum gravity will be a deformation of a special relativity. Following this line of arguments, one can consider first the simplest possibility is just a Lorentz invariance by a violation of Lorentz invariance. But okay, this is in fact the simplest and most studied possibility to deform special relativity. But it requires to consider some privileged reference frame or a set of reference frames that usually are identified with or are related with the homogeneity and isotropy of the cosmic microwave background. But there is an alternative, which is to try to deform special relativity while keeping the relativity principle. Now the story starts 20 years ago with the first papers where a proposal to make the presence of a minimal length scale, or which is a characteristic of many of the proposals for a theory of gravity, of quantum gravity. Okay, to make consistent the presence of a minimal length with or to escape to the incompatibility of such a fixed length scale with Lorentz invariance, with Lorentz transformations. Now this leads to the idea that okay, to deform these transformations in some way. To have, okay, in fact, to have an energy scale invariant under these transformations, and the main ingredient of this of the realization of this idea is the non-trivial step going from a single particle state to a multi-particle state, even in the case of a free multi-particle state. And this non-trivial step comes through a relation between the total energy and momentum of the multi-particle state and the energy and momentum of the particles, which is not simply the sum, but has some corrections with some new energy scale, lambda. Together with this kinematics of multi-particle state, one can also have modification of the energy momentum relation of a particle. Now, this relativistic deformed kinematics can be understood from different perspectives, in complementary and consistent perspectives. The first one is one can try to derive relativistic deformed kinematics from the geometry of a maximally symmetric momentum space. The idea is that the deformed Lorentz transformations are related with isometries in this maximally symmetric momentum space. translations in this curved momentum space are related with this deformed composition of momenta, which is not simply the sum. The energy momentum relation in the relativistic kinematics of a particle is associated with the square distance from the origin to a point in momentum space. And there is also some generalization of a space-time, for which one has two alternatives, either to consider generators of translations in momentum space or vectors in tangent space. Another perspective of relativistic deformed kinematics is based on the notion of locality. In fact, it can be easily identified that the deformation of the composition law of momenta, of energy and momenta, in the multiparticle state realization implies immediately a loss of locality of interactions defined by the energy momentum conservation with this deformed composition law. Now, this loss of locality can be interpreted in two different ways. On the one hand, just as a way to go from the notion of absolute locality in special relativities to relative locality. I mean, to locality only for some observers. I mean, in fact, from all the observers related by translations, only one of them see an interaction as a local one. Another alternative is just to try to identify this loss of locality as an
sorry, there are 5 minutes left.
Thank you. Thank you. To the necessity to go to a generalized space-time. Another third perspective is an algebraic one. I mean, it's a generalization of the understanding of symmetries in the algebraic, in the Lie algebra formulation to the case of a non-commutative space-time, replacing Lie algebras by Hopf algebras. And in this algebraic context, one finds algebraic ingredients, which in fact can be put in one-to-one correspondence with the ingredients of relativistic deformed kinematics. There is no, as I said at the beginning, there is no consistent theoretical framework incorporating this idea of relativistic deformed kinematics, and this means that as a consequence, one has many open questions that still have to be clarified. Here is one example of some of these questions from a theoretical perspective. The first one is that the deformation introduces an arbitrariness in the choice of energy momentum variables. What means energy and momentum? Another one is the domain of applicability of the relativistic deformed kinematics. It is obvious that this relativistic deformed kinematics cannot be applied to any system like special relativistic kinematics, because then one finds obvious inconsistencies. In fact, this is related with the part and the whole of this meeting. I mean, where to what kind of systems can this deformation will apply? Third one is that there's no dynamical framework. I mean, it is not. We still don't know how to incorporate relativistic deformed kinematics in the quantum field theory framework. There are several attempts, but still is an open question. And also, as I mentioned before, the space-time is also not clear. I mean, this is related to the interpretation of this loss of locality. from the phenomenological perspective, very important one is how the deformation is reflected at the level of observables, especially in space-time. The question of physical energy momentum variables. I mean, it is just a phenomenological task to identify what are the energy momentum variables. Also, another point is that the kinematics, if you study the kinematic of particle processes and the effects of a relativistic deformed kinematics, you find that this deformation is relevant only when the energy of the particles in the process approach this scale of the deformation. Now, if you accept the naive argument that the scale in quantum gravity should be the Planck mass, then this makes all effects of relativistic deformed kinematics completely unobservable. And also related to the absence of the dynamical framework, okay, one can consider toy models for the dynamics that I don't have time to describe. Okay, all this leads to a research project which we are involved, which is on the one hand, okay, which is also motivated by new windows of observation in high energy astrophysics that we plan to explore the possibility to identify where we plan to explore the possibility to identify effects of this deformation of relativistic kinematics and they can show up in near future new observation of extremely high energetic neutrinos, or in an improved understanding of very high energy cosmic ray spectrum, or in new observation of high energy gamma rays. And also let me point out that even if you forget all the arguments to relate or to think that a relativistic deformed kinematics can be a signal of quantum gravity, one still can think of relativistic deformed kinematics as a possible way to go beyond the actual paradigm in particle physics, which is relativistic quantum field theory, and perhaps this can give a new perspective of some of the indications of its incompleteness. Okay, it would have been much better to be in this nice place during the warm summer in Chile instead of being at home in the cold winter in Spain. But this is the way life is. Thank you.
Okay. Thank you very much, José Luis Cortés, for the nice talk. Is there any question? Okay, okay.
Okay. I have
Maria.
Maria, want to talk? Yeah.
Yes, there are questions. Maria Pilar, can you please?
Hola, José Luis.
Hello.
Did you very nice talk? You have said at the very beginning, but I am not clear. In your relativistic deformed kinematics, are you assuming that you have Lorentz invariance violation or not? This you said, no, but I didn't understand.
No, it's a deformation. I mean, you have inertial reference frames, like in the case of special relativity, but the transformation which relate these reference frames are deformed, okay, but they are there. I mean, so there is no violation in this sense. Okay. In the case of violation, you don't have, you lose all these reference frames, and you select either a particular one or a set of reference frames if there is a subgroup of the Poincare invariant.
No, yeah, because I was thinking that if in that case, if there was any relation with Jorava gravity, but if you don't have, then obviously not.
No, it's a different scenario. Yeah.
Yeah. Thank you.
Mauro Cambiaso has a question.
Yes, thank you, José Luis, for your nice talk. My question was related to this transformation between inertial observers, because as far as I remember, there is one maybe similar scenario, this doubly special relativity, in which you had different transformations between observers, and there was a problem with the intensive property of energy, like the sum of the energy of the two systems was not equal to the sum of the to the energy of the sum. So my question is whether in your relativistic deformed kinematics, do you have a similar problem? Because you still have deformed transformations.
Yeah, sure. I mean, in fact, it is, as I said, I mean, it is the key ingredient of the relativistic deformation. I mean, is that the total moment, the total energy and the total momentum is not just the sum.
Okay.
I mean, for a system of particles.
Mm-hmm.
Yeah, in fact, all the kinematics can be derived from this starting point.
Okay, we have a question of Joaquin also.
Okay, I would like to understand if there is some sort of relation with very special relativity and deformed very special relativity, where there is also, in the case of deformed very special relativity, there is a non-trivial and non-local Marshall condition. And I thought you were saying that when we have that, will be some signal of quantum gravity. And I don't, to my knowledge, I don't know if anybody has tried to connect this deformation of very special relativity with quantum gravity. At least in attempts that was done in the past, was not completely obvious that this deformed very special relativity is compatible with the Sitter space, for example, with a curved space.
I'm afraid I am not. I don't know enough about this deformed very special relativity. I know about very special relativity. It's not. It's a different idea. I mean, it's to have a subgroup. I mean, in a sense, it's violation of Lorentz invariance because you don't have. You don't have the one-to-one correspondence between inertial. Between inertial frames in very special relativity and in special relativity. It's a subgroup. Deform, I don't know, in the case of deformed very special relativity, I don't know the deformation, how it is implemented. So I'm afraid I'm not able to answer your question.